The second speaker is Professor Cristina Costantini from University of Chieti-Pescara. She will speak us about obliquely reflecting diffusions in curved non-smooth domains. Enjoy the talk.
So, good morning. First of all, I would like to thank the organizers of both the anomalous diffusion semester and the stochastic reflection networks for their very kind invitation. It's a great pleasure for me to be here. And I'm going to, as you know, I'm going to talk about obliquely reflecting diffusions in curved non-smooth domains. And this is joint work with Tom Kurtz. Okay, so, do I get this right? No. Oh, oops. Not working? Okay, maybe no. How this work? Sorry. The down button is the next one, sorry. Okay, so most of the times we hear about reflecting diffusions in actually polyhedral domains. And in this workshop too, we have heard quite a bit about reflecting diffusions in polyhedral domains. So let me give you just a little bit of motivation for looking at reflecting diffusions in non-smooth curved domains. So motivation comes, for instance, from networks, from this is a paper by Kang and Williams, where the diffusion approximation to the rescaled workload process is conjectured to be a reflecting diffusion in this cone. That is a piecewise smooth cone, okay? And the same happens, well, I guess mine's, well, down is next, right? Well, maybe, you know what, I stand here, maybe that's easier. Let me just see, yeah, okay. At least I'll move over here, okay? Sorry. So this is another example from stochastic networks. And again, the diffusion approximation of the rescaled workload process is going to be, it's conjectured to be a diffusion approximation in this piecewise smooth cone. And in this case, besides being a piecewise smooth cone, the faces of the cone meet in cusps. This is the example I was, talking about yesterday in the open problem session. Let's see if it can work. No? Oh, yes. So then this is another example. This comes from stochastic, singular stochastic control theory. So in this paper that's cited above, the candidate for the optimally controlled process is a reflecting diffusion in a domain that looks essentially like this. Okay. So I'm going to focus on semi-martingale reflecting diffusions, or semi-martingale obliquely reflecting diffusions. So there is, of course, a very vast literature on non-semi-martingale reflecting diffusions. And we've heard quite a bit in this workshop about non-semi-martingale reflecting diffusions. But as I said, I'm going to focus on the semi-martingale case. And I'm also going to exclude normal reflection. So, or if you like, it's a special case, but the focus is not on normal reflection. So there is, of course, a very important literature on normal reflection in very general domains, extremely general domains. So in our formulation, so a semi-martingale obliquely reflecting diffusion is a solution of a stochastic differential equation with reflection, where you have to think that in our formulation, at each point on the boundary, there is a prescribed cone of directions of reflection. And the term on the boundary is this, of course. It's an integral against lambda. Lambda is, as usual, a non-decreasing continuous process that increases only when the process is at the boundary. And this gamma process is a process that at every time takes values in the cone, in the reflection cone. Okay, and it's normalized to 1. So, that's a problem. Okay, sorry. Yeah, I'm really, no, let's see. Not very good at this. Okay, but I had to go up one. No, wrong again. Okay. So sorry, sorry about that. I'm really clumsy. I think this should be, this is the right one. No?
Let's go to the right. Go to the right with the 3 dots. Click on more.
Click on more all the way there. Yes,
Yeah.
great.
There's hide.
Hide.
Oh,
Hide fleeting meeting control. So floating meeting. Okay. So okay. Also, if we restrict to semi-martingale obliquely reflecting diffusions, again, there is a very vast literature. But in my view, the state of the art is given by 3 papers. The first of these papers is the paper by Kwon and Williams that has to do with the tree that deals with a smooth cone. Okay, they characterize obliquely reflecting Brownian motion as a solution with a martingale problem, and they have a very complete treatment. They don't discuss in this paper whether the solution is a semi-martingale, but actually it comes out of we have a result in one of our recent papers which shows that this is the case, which shows, gives a sufficient condition for the solution of the submartingale problem to be a semi-martingale. Then the other paper is the Dion-Williams paper in convex polyhedron with constant directional reflection on each face, which also gives sufficient conditions for existence and uniqueness of semi-martingale obliquely reflecting Brownian motion. And these conditions, the conditions they give, are actually necessary in a simple polyhedron, okay? Necessary for existence of obliquely reflecting Brownian motion. And then, last but not least, of course, there is the Dupuis and Ishii paper on piecewise C1 domains. Now, this is a very, it covers a lot of cases, and it's a great paper. We, actually, we've drawn a lot from it, but it happens that it leaves out some significant examples. Okay, I mean, the assumptions in the paper leave out some significant examples. So let's see if I can make this right. No, apparently I don't understand why it doesn't work. Maybe I should point there. Well, okay. Okay, no. Yeah, è quello che stavo facendo. I usually don't have so many problems with technology. Okay. Okay, va bene. Okay, so these are these are some examples where the Dupuis and Ishii conditions are not satisfied. This is a very simple two-dimensional example. In that example, they're not satisfied. Essentially, the reason is that the Dupuis and Ishii conditions essentially are conditions on the absolute value of the angle between the directional reflection and the normal direction. So if you have a situation where one direction points toward the corner, another direction points away from the corner, you can have situations where you can actually get existence and uniqueness of the process that are not covered by their, by their conditions. And also, their conditions do not allow for cones, for any type of cones. So the examples from the stochastic networks that we had seen before are, have to be dealt, were not covered by the result. So, what I want to do today is show you how a recent ergodic theorem that Tom and I proved can be used to get uniqueness for some of these examples that are not covered by Dupuis and Ishii. And I'm going to focus on 2 classes of examples, 2-dimensional piecewise smooth domains. Here we have a very general, I think, a very general condition, and then some piecewise smooth cones. Okay, so here is what I mean by a piecewise smooth domain in R2. It's the intersection of a finite number of domains with a C11 boundary. C1 with a Lipschitz condition on the normals. And I'm going to assume I of X is the set of indices, that tells you to which faces a point X belongs. And so since we are in R2, I'm going to assume that this is like a minimality condition. At every point belongs either to one face or to two faces, to one side or two sides. And the set of singular points that I'm going to call corners is finite. GI of the, on every side of this domain, you have a direction reflection, and the cone, the reflection cone, is the cone generated by the directions of reflection at the faces that the sides that meet at this point. So okay, then it turns out that all the singular points can be classified in one of these three cases. The first two cases, okay, either the two normals are independent, linearly independent, or they coincide. In this case, you may argue that, actually the domain, the boundary is smooth at that point. The boundary is going to be C1, but you might have a discontinuity in the direction of reflection. Okay, so this is why, and there are actually examples coming up from stochastic networks where this type of situation comes up. But in these two cases, as you see, the normal cone, in both cases, the normal cone will not contain a straight line. And then you may have a cusp. In this case, of course, the directions of reflection are opposed. And so the normal cone, which with our definition is going to be the right half plane, it has, of course, contains the full straight line. Okay. Now our benchmark is the Diane-Williams paper, which I'm going to rephrase a little bit. I know I'm not sure Ruth agrees with the rephrasement, but we can talk about it later. I like to rephrase the result in this way in two dimension. The assumption is that at every point on the boundary, there exists a vector in the normal cone that forms an angle of strictly less than pi/2 with all directions of reflection. Okay, this is actually equivalent to the condition that is stated in Diane-Williams paper. So if you have this, then the solution is unique in this, exists and is unique in distribution. And as I said before, this condition is necessary for existence of obliquely reflecting Brownian motion. So here is our result for piecewise smooth domains in R2. Okay, we have standard assumptions on the coefficients. We need the dispersion metrics to be non-singular at corners. And then, as you see, the main assumption is exactly the same as in Diane-Williams. And so it's the assumption that you have this E vector that forms an angle of less than pi/2, strictly less than pi/2 with all directions of reflection. So under this condition, again, you have uniqueness or for the solution of the SDER. Now, since we are dealing with cusps as well, I would also like to mention that in the case of, there's a very well-known paper by de Blasi and Tobey on cusps, and our condition is essentially coincides with theirs, in the sense that in their case, they have a little more specific case, a little more specific type of cusps, and they have directions of reflection that are, constant with respect to the normal on each side. However, our condition coincides with theirs almost perfectly in the sense that there's just one case where they have a slightly more general condition. But for most cases, so, sorry? Okay, I'm focused on uniqueness because I want to show you how this ergodic theorem comes in, and that comes in in uniqueness. But we do have unique existence under the same assumption. Okay? In dimension 2, if you try to do things in higher dimension, then you need a little bit. Now, these are two examples that would be covered by our theorem. The one is the example that I mentioned before. And this is another, this would be like a two-dimensional cross-section of those cones that we have seen at the beginning, okay, and that I was talking about yesterday as well. So, now, as I said, since I want to show you how this ergodic theorem comes into play and how it allows you to prove uniqueness, I want to actually, give you an idea of the proof because I want to show you how it comes in. Of course, the proof has various steps. So we will go through various levels of reduction till we get to one core point where the ergodic theorem comes in. So first reduction is localization. Of course, we can, we can cover the domain D by domains that have just one single, each of which has just one, the boundary of each of which has just one singular point, includes only one of these corners or cusp points, okay? And the domain elsewhere is smooth. The boundary of the domain elsewhere is smooth, okay? So we can cover D with these domains, the boundary of which has just one singular point. So this is the first reduction. And actually the results we have hold in higher, in general dimension, as long as you restrict yourself to domains that have just one singular point. So, so this is the first reduction. Then the second reduction is that since there is just one singular point, if you start at a different point in the domain, so now we are in a domain which has just one singular point. If you start at, and the singular point from now on is the origin. If you start at any other point, as you can imagine, the boundary is smooth elsewhere. So until you hit the origin, until you hit the singular point, the distribution is actually uniquely determined. So we can reduce, in order to prove uniqueness, we can reduce to consider only solutions that start at zero, at the, the singular point. And the next, another reduction is that we can reduce to proving uniqueness among strong Markov solutions, because one can prove that if you have uniqueness among strong Markov solutions, then you have uniqueness among all solutions. And we're going to use this. So we will deal only with solutions starting at zero and that are strong Markov. And all of these solutions have two properties that the first property is that, since they are solutions of an SDR, so they're semi-martingales with a quadratic variation absolutely continuous with respect to dt, then they, all these processes by definition will spend zero time at zero. And actually, implicitly, the vector, this is one place where the vector E implicitly comes in. The other, sorry, sorry. The other place where the vector E comes in is that it ensures you that a solution starting at zero will leave any bounded neighborhood of the origin. Okay, and the expected time that it takes the solution to leave this domain, so to get to this boundary, is finite. This also comes from the vector E. So this is where that assumption comes in these 2 points. Now, so we know that all solutions have these two properties, and these two solutions allow to prove that if you take, for any two solutions, strong Markov solutions starting at zero, if for some family of neighborhoods of zero that shrink to zero as delta goes to zero, so they could be balls like here, balls of radius delta that shrink to zero. If for all of these neighborhoods, for all deltas, the heating distribution of the heating distributions of the two solutions on the boundary are the same, okay? Then actually the law of these two processes is the same. So then we have uniqueness among strong Markov solutions starting at zero, and by what I said before, that's enough to have uniqueness among all solutions. Okay. So, now here we come to the main point. How do we prove that? Well, we actually we have a yes, because it's a little bit long. We actually show that there exist strong Markov solutions, which is not obvious because you don't have uniqueness a priori. So we actually show that, you know, it's like, yeah, I have to show you. We have it, but it's not obvious. You have to use the Markov selection theorem. We have, and then with the Markov selection theorem, you also get that uniqueness among strong Markov solutions is the same, gives you uniqueness among all solutions. I don't know if that really, basically it's a Markov selection. Now what is the intuitive idea now? Okay, now we are reduced to proving that any two solutions starting at 0 have the same heating distribution here. This is the boundary of U delta, okay? So this is the boundary. We fix a delta now, an arbitrary delta, because we want this for every positive delta, or every positive delta small enough. And we fix a delta, and we want to show that any two solutions have the same heating distributions here. So what we do is we consider a sequence of layers that are, in some sense, rescalings of this boundary. In this case, in this picture, they are exactly rescalings of that boundary, but we'll see in a minute that they're not always exactly rescalings, but essentially they're rescalings. We take and we construct in this way a sequence of layers from E0 up to, say, En, or down here. And what we do is we look at the solution is starting at 0 and it's going out of all these neighborhoods because of what we said before. So we look at the heating position of the solution on all of these layers. So, here is the heating position on the first layer, next layer, and up to here. And this, of course, this is a Markov chain because we have a strong Markov solution. But we want to look at the killed Markov chain. So we want to look at this Markov chain killed if, in going from layer En to layer En minus 1, the solution hits 0. We kill it if it hits 0 in between. Okay? If in between going from one layer to the next one, it hits 0, it gets killed. And the reason we want to do that is that since the distribution of the solution is uniquely determined up until when you hit 0, if we kill the chain, it means that the Markov chain will have a uniquely determined transition kernel. Okay, because the transition kernel only depends on the distribution until 0 is hit. Then if you hit 0, you get killed. Okay? So the transition kernel is uniquely determined. So now if we take two solutions starting at 0, so we get two Markov chains, psi h and psi tilde h, that are the positions on all these layers of these two solutions. These two killed Markov chains will have the same transition kernel, but since they are starting on layer En, they will have in general different initial distributions because we don't know yet that any two solutions have the same heating distributions. Okay? So we have to assume a priori that when the two solutions hit layer En, they have different distributions. And these are the initial distributions of these Markov chains, these killed Markov chains. So the idea, but of course, this layer En is going down to 0. We can take, we can make this chain longer and longer by taking the initial layer En closer and closer to 0. So, and as I said, these chains all have the same transition kernel. So if in some sense, but we actually have a family of transition kernels because these Markov chains are inhomogeneous. They're not homogeneous Markov chains. So we have a different kernel for each step. But if in some sense this family of transition kernels is ergodic, then what we may hope is that in the limit, as we take En closer and closer to the origin, so we make the chain longer and longer, in the end, the initial distributions on En should be forgotten, right? Because if it's ergodic, it should forget its initial distribution, which means that the two Markov chains should have the same limiting distribution, but their limiting distributions are just the heating distributions on this fixed final layer. Okay, and so then we are in business. Then we will know that the heating distributions are the same. Okay, so how do we make this rigorous? Of course, this was extremely heuristic. The way we make it rigorous is this. Okay, this is the transition kernel of the two Markov chains. Now, one can prove that the expected value of a continuous function on the final term of the Markov chain, of both Markov chains, is this ratio. And of course, the two ratios for the two Markov chains corresponding to the two solutions are the same, except for these starting initial distributions mu n and mu tilde n. And as I said, of course, this is the position on the final layer on E naught. So it's just the heating distribution of the solutions of the SDR starting at 0. So if we can show, so this, where one proves this, and then if one can show that these fractions here have a limit as n goes to infinity, and the limit is independent of the sequence mu n, then if these two things have this, these two things are actually equal for every n to these, so these two expectations will be the same. So, here is here is in fact the theorem that states that in fact this limit exists and is independent of the sequence of the initial distributions. We have two assumptions. I'm going to comment on the assumptions in a minute. The two assumptions are essentially two lower bounds. Okay? One is a lower bound on this quantity epsilon k, a uniform lower bound on this quantity epsilon k, and the other one is a uniform lower bound on this ratio. Okay? So how can we read these assumptions? Well, it turns out that this quantity epsilon k is actually bounded from below by the maximum of the total masses of these two measures. So these are the transition, this is the transition kernel. You start on a point x, from a point x on layer ek, and you go to layer ek minus 1. So this is the total mass starting at x, and this is the total mass starting at x tilde, and these are killed Markov chains. So these things are not one in general. So the maximum of these two total masses minus the total variation distance between the two measures bounds this quantity epsilon k from below. So if we can show that this difference, has a uniform lower bound, we are in business. And showing that this difference has a uniform lower bound means that the total variation distance between the two measures, starting at x and x tilde, is less than the maximum of the total masses minus some positive number, small positive number, which I'm sure you can now recognize as a typical ergodicity condition, okay, in this form, I think. So we obtain this by a coupling lemma in the spirit of Lindvall and Rogers, and a scaling result that I'm going to talk about in a minute. So this is, we're going to talk more about this, how you get this in a minute. The other condition, so this is a condition on the one-step transition kernel. For every k, we have a transition kernel. This condition only concerns the one-step transition kernel. The other condition you have, that this ratio must have a uniform lower bound, has to do with the n-step transition kernel, because you see in the numerator and the denominator, we have this n-step transition kernel. So this is the total mass of going from a point x on layer En up to E naught. Okay, so it's n steps. And okay, so in general, when the origin can be reached, both the numerator and the denominator here go to 0. Because you know the probability of hitting E naught, as you start closer and closer to the origin, the probability of hitting E naught before the origin goes to 0, of course. But what we ask is that the ratio between these two probabilities is uniformly bounded from below. Okay, so this is what we ask in this, in what one proves. Okay, so let me tell you a little bit about the scaling. In particular, because the scaling is where you see the difference between the cone case, between having a cone point, if you like, a more regular, a cone point, or is a cusp point, because the scalings are different for cone points and cusp points. So for a cone point, we can take this family of neighborhoods, U delta, to be just the intersection of balls with the balls centered at the origin with the domain. And and then the rescalings are, exactly rescalings of the boundary of the ball. So, these are boundaries of balls of radius rho to the k delta, where rho is less than 1, because they have to go to 0. And it turns out that now, if you look at the rescaling of the solution, you take a solution of the SDR, starting from a point that, after rescaling converges somewhere, and you rescale it in this way. So you look at the solution for a very short time on a very fine time scale. So you blow up space, short time, blow up space. In the limit, what you get is a reflecting diffusion, is a reflecting, in fact, a reflecting Brownian motion with 0 drift in the cone that is tangent to your domain at that point, because in what I call cone points, there is always a tangent cone. In the degenerate case, this will become a half plane, but it's always a cone. So it's either a half plane or a, strictly speaking, cone. So you get this, and from this fact that you have this limit, you can get the lower bound on the epsilon term. Okay, you have to use this coupling tree. Okay, you have to construct a coupling tree. But what is now? This is instead the situation for the cusp case. In the cusp case, the domains we have to take are, you fix a point delta, a number delta actually on the x1 axis. Here is your cusp. You fix this number delta, and you take as a domain U delta the intersection of the plane, of the half plane left of delta with your cusp. Okay, so this will be U delta. And so the boundary of U delta is just this vertical segment. And then you want to construct this sequence of layers that in some sense scale down to the origin. So how do you construct them? At every step k, you are at some delta k minus 1. You look at the distance between the two sides of the cusp, this qk, and then you move left by qk. By qk. Okay? And this is going to be the next delta k. So the next delta k is delta k minus 1 minus qk, and qk is the distance between the two sides of the cusp. So you do this, you take this situation, and then what you see is that if you take, again, you take your solution, your rescaling factor, so this is just, the solution has two components, first and second components. Your rescaling factor is qk. And you take a diffusive rescaling, of course. For the second component, it's okay. For the first component, you have to subtract delta k because qk minus 1 delta k goes off to infinity. Okay, so if you don't subtract this delta k, you're not. This x1 is on the level, x1 is here. Okay, so x1 is actually, sorry, x is here, so x1 is actually delta k. So if you don't subtract delta k, you're going to get infinity there. You know, everything kind of washes out to infinity. So you center the first component in this way, and then you have a limit. You end up with an obliquely reflecting Brownian motion in this infinite strip. With zero drift and with the directions of reflection that are just the the directions of reflection you would have at zero. The two limiting directions of reflection you have here. So sorry, 1 second. So again, this limit result, this rescaling, this limit result is what allows you to, combined with this coupling, allows you to get the bound on the epsilons. So now let's look briefly at how much I have. Oh, good. Okay. So, okay. So now let's look at the other assumption, briefly at the other assumption, the assumption on the n-step transition kernel. So the assumption says that we have to find, the assumption consists in showing that you can find, if you want to apply the theorem, you have to show that you have this uniform lower bound on this ratio. And okay, this is the total mass of the n-step transition kernel from a point x on En to the final layer E naught. So this is, of course, just the probability that you hit, that starting at x on the layer En, you hit the external layer E naught before hitting the origin. So this quantity here is this probability. And you want to have, you take the infimum over all points of En in the numerator, the supremum of points in En in the denominator, and you want to ensure, you want to make sure that this ratio has a uniform lower bound, uniform in X and in N. Now, of course, if things were smooth, one could actually compute, the probability. This probability would be a harmonic function. But we are looking at a domain that is not smooth. So in general, one doesn't know how to do this. But here is but you can make the following observation, which is actually, I think, similar to an observation that Rami did in his talk, that after all, we are looking for a lower bound. So all we need is to bound this probability from above and from below. We don't really need to know it exactly. We just need to bound it from above and from below. And so it is sufficient to find, so it is sufficient to find two functions that satisfy corresponding inequalities, okay, with respect to this PD problem. Okay, so one with minus or equal, and the other one with plus or equal. And in addition to this, they will have to satisfy another condition that other two conditions that I'm going to, write in a minute. Okay, of course, I forgot to mention that you need this only if you don't, if you can hit the origin. So basically, either you are in a situation where you cannot hit the origin, starting, of course, at another point, which, it means that at every point other than the origin, if you are inside this neighborhood U delta, you're going to hit the boundary of U delta before the origin. Okay? This means that you're never going to hit the origin if you always hit the boundary of U delta before the origin. So either you are in this situation, and this you can also, verify, at least you can have a sufficient condition for this by another Lyapunov function like this. Or if you are not in this situation and you actually can hit the origin, then you need to find, if you find two functions like this, you will still be able to obtain the lower bound you need. Okay. So, and this brings us to piecewise smooth cones, because I forgot to mention that actually, whenever you have a domain with just one singular point, under the assumptions we've made, that is that there exists this E vector, it is always possible to construct these functions. Okay, either the function V that ensures that you never hit the origin, or these two functions. And the way you construct them is by leveraging, by suitably perturbing the harmonic functions that are in Kwon and Williams' paper. Okay, for the cone case, and for the cusp case is actually even easier because, well, because in order to have a semi-martingale, you essentially must not hit the origin. But so in the most interesting case, that is actually the cone case, you just perturb, you perturb in a way, in some suitable way, the functions that are in Ruth Kwon and Williams' paper, and you can always construct these functions here. But in the case of piecewise smooth cones, there is no general way to construct them, or at least I haven't found. I haven't found any general way of constructing these functions. So what we have to do, we will have to assume that one can find these functions and find them in every example. So, and I will give you an example where I could find it. Okay. So, so this brings us to piecewise smooth cones. So a piecewise smooth cone is the intersection of a finite number of smooth cones with C2 boundaries. Again, okay, and we are going to, okay, of course, we are in a cone, so the normal vector is uniform along each radius. And it actually coincides with the normal vector on S D minus 1. I of x is the usual, the set of indices of all the faces that meet at a point x. We assume that the normal directions are at every point x other than the origin. The origin is the vertex of the cone. The normal vectors at all other points are linearly independent. So then, as I said, we have to assume that these Lyapunov functions exist. I mean, for every example, we have to find them. So either we have to find a function that satisfies these inequalities and blows up at the origin. And this will be the case, you know, if this function, if you can find this function, then starting off the origin, one never hits the origin. Or one has to find two functions that satisfy the inequalities we were talking about, you know, that we saw before. And in this case, these two functions must go to 0 as x goes to 0. They will typically not be smooth at 0, but they have to go to 0 as x goes to 0, and they have to go to 0 at the same rate, essentially. Okay, so you must have, if you look at the ratio between these two ratios, the infimum of all, you know, of all of these two ratios, of each of these two ratios has to be strictly positive. Essentially, it means that the two functions go to 0 at the same rate. So, so now we assume this, and here is the theorem. Suppose you can find these Lyapunov functions, and suppose that at every point on the boundary of the piecewise smooth cone except the vertex, you have this condition, this matrix that takes into account all the inner products between directions of reflection and normal directions, has spectral radius less than 1. This condition is a sufficient condition for Dupuis and Ishii condition. Okay, the Dupuis and Ishii condition is a little bit more general, but it's very hard to verify in its general form. This is the sufficient condition that is often used to verify the Dupuis and Ishii condition. So essentially, we have to assume that at other points, the Dupuis and Ishii conditions are satisfied. And then here is the assumption we have seen all the way along, that in this case, at the origin, there is a vector in the normal cone that forms an angle with all directions of reflection, which are now infinitely many. There are now infinitely many directions of reflection, of course, at the origin, because the directions of reflection will, in general, will change, will vary on each smooth face. So you have a direction reflection on each smooth face that varies along the face. So at the origin, you have, the limits of these directions of reflection. There are infinitely many of these limits. They form this cone, reflection cone at the origin. So you must have this vector. And then in this, you can, by the ergodic theorem that I showed you before, you get uniqueness. You can satisfy all the conditions of the theorem. So here is an example from bandwidth sharing networks. We have a network like this. I'm not going to get into the details of how a bandwidth sharing network works. However, you have 3 resources and different routes. Some of these routes will use each route uses some resources. In this specific example, we have 3 routes that use, this is from the Ken, Kelly, Lee, and Williams paper. It's an example that I took from there. So you have 3 routes that go through just one resource, and then you have 1 route that goes through all the 3 resources. And on each of these routes, there are documents that are transmitted that have an exponential length. So these documents use up simultaneously all the resources. So the documents on Route 4 will use all the 3 resources. And so they arrive at Poisson rates and, and spend, have an exponential length. So spend an exponential length of time in the system. So you need a policy to allocate the resource at each of these nodes among the different routes. You find this policy, actually, it's found in this paper. And then we go to a heavy traffic. So we assume that these arrival rates and exponential, exponential rates depend upon a parameter R. We are in heavy traffic. And in this example, I want to consider, just to make things simple, we assume that the limiting arrival rates are 1, and the limiting service rates are all, or exponential length rates, sorry, are all 1 except 1. Okay, this is the exponential rate of this route. Okay, this we're going to leave free, as a free parameter mu. And in this problem, there is a very important parameter, which is this alpha. That is not the alpha in Vardan and Williams' paper. It's a different parameter. It's actually an exponent that appears in the optimization problem you have to solve to find the optimal policy. So, so then, it's in the Ken, Kelly, Lee, and Williams paper, it's conjectured that the rescaled workload process converges to a reflecting, obliquely reflecting Brownian motion in a cone D. The shape of this cone depends on the parameter alpha. If alpha is 1, the cone is a polyhedral cone, and one can use Routh results to prove the diffusion approximation. If the parameter alpha is less than 1, you get a cone where the faces meet in cusps. And if the parameter alpha is larger than 1, you get a cone where the faces meet in, in this, in corners, okay, in this way. The directions of reflection are just, unit vectors parallel to the axis. So you have on the green face, the direction of reflection is G1, is in this direction. On the blue face, which is this, it's in this direction. And on the red face, it's up. So, for this example, it turns out this is the dispersion matrix. So now the directions of reflection are fixed, but the cone depends also on the parameter mu. What happens is that, maybe I should go back. What happens is that as mu increases, the cone kind of opens up. And as mu goes to 0, the cone closes up till it kind of shrinks to a single line, to a single half line. So this is the example. If alpha is larger or equal than 2, and if the parameter mu is larger than this threshold, one can find this Lyapunov function, actually minus log of modulus of x, which is a typical Lyapunov function, works. And then, so everything goes through, and you know that the solution is going to be unique. Okay, so you have a unique characterization of this obliquely reflecting Brownian motion, this piecewise smooth cone. And okay, the solution has this property that if starting at 0, it immediately leaves 0 with probability 1, and starting at another point, it will never reach 0, as I said. Okay, okay. And so I guess now, well, maybe I actually had prepared something on existence, but maybe. Okay, so maybe I can just tell you a little bit very quickly on the existence part. On some of our existence results. We have some existence results for piecewise smooth domains. Okay, this is the type of existence results we have. Okay, we need, okay, for our existence results, we need another condition that is a little bit harder to, okay, we need this condition here. Okay, for every point on the boundary, now we are in dimension D. At every point on the boundary, we have this set of the indices of all the faces that meet at point X. And we want, so this is a set, set of indices, but we want to look, we need to look at some subsets of this set of indices. That are, so this is a family of subsets of this set that, these subsets correspond to sets of indices of points outside of the domain, where the set of indices for points outside of the domain is defined to be, this is an intersection of domains. So a point outside will belong to some of these, but not all of them, otherwise it will be inside. So this set of indices for points that are external to E is actually the set of all the domains to which Y, in this case, does not belong. So we look at these subsets, and we break the reflection cone and the normal cone, we break it into subcones, okay? Or we look actually at all these subcones of the reflection cone and the normal cone. And then, so now this condition has to be formulated in this way, that at every point on the boundary, in practice, what happens is that there are examples where you cannot actually require okay, sorry, no, you still require this just as before, that there exists a vector E in the normal cone, etc. But then in a higher dimension, not in dimension 2. In dimension 2, this is enough. But in higher dimension, you need this other condition. That is, you need, in some sense, the dual condition with respect to this, in the sense that you need, in some sense, to have a normal that has forms an angle of strictly less, you need a direction of reflection that forms an angle of strictly less than pi/2 with all the normals. But if you are going to require this for all the normals, you're going to cross out all cusps. So you don't want to do that. But you can weaken the assumption in this way. This will allow you to get to include cusps. So you are going to require this, that in all of these subcones, you can verify this, but in each of these subcones, okay? So for every of these subsets, you look at you need to find a G in the subcone of directions of reflection, that has positive inner product with the normals in the corresponding subcone. So this will allow to deal with cusps as well. And then, yes, and then you get this, you get existence, and you also get this. Okay, now if in the case of a simple convex polyhedron, this condition that looks very complicated actually agrees with the Diane-Williams condition. So the key points of the proof is that here, for existence, you want to use these constrained martingale problems that Tom Kurtz invented many years ago. They're helpful in the existence part. They are not so crucial for uniqueness, for what I told you about, for what I spoke about before. But they actually, at least we feel, they're useful for existence because they allow you to avoid proving oscillation or estimates. Okay, if you follow this constrained martingale approach, you don't have to prove oscillation estimates. And as long as you're in a bounded domain, it is not so terrible to verify what you need to use the constrained martingale problem. It becomes a lot worse if you are in an unbounded domain. Okay. So yes. So what is a constrained martingale problem? Actually, it's a martingale problem where you have the usual term and then you have this boundary term. If you subtract it, you're going to get a martingale. Okay. Of course, if you and then what you're actually interested in is what are called the natural solutions of this. That are solutions of some of another martingale problem that is a slowed down version of the martingale problem, just to give you a rough idea of what this is. So you construct solutions to this by first constructing solutions to a slowed down problem. And from there you go back. Okay, that's enough, I'm sure. Sorry.
Okay, so we have 1 minute for question.
Yeah, sorry.
Is there any question from? Oh, okay. Question here.
No, it's what Tom originally called it. He called this a controlled martingale problem. It's just the terminology because he was thinking of, in some sense, you think of these. You see here, you have in a controlled martingale problem, you have like a term that is a slowed time, it's a slowed down time in the interior of the domain, and then you have this measure here, and he thinks of these U's as values of a control. Okay, so the idea is that when you're on the boundary, you have you have a control that pushes you in some sense.
And can I have another question? And do you have so you proved uniqueness among semi-martingale solutions?
Yeah.
Can you extend it to the broader class of solutions to the sub-martingale problem? Does uniqueness hold immediately also for this potentially larger
yes,
set of solutions?
Well, okay, I think that, Okay, for the uniqueness part, okay, for the ergodic theorem, I think it's possible that it could be used. I'm not sure, but if you restrict yourself to solutions that spend zero time at the singular point, because you need that, and if you can show that, so it's possible, but I've never really. Pardon?
It's not automatic.
No, not at all. Not as far as I can see.
Further questions? People from home? If no, let's thank the speaker again.